Okay, while we waiting for my colleague to share the slides, let me just briefly tell the introduction. So my name is Ayana, and we're team MBZ UAI, DSMLKZ, lots of words. We're from MBZ UAI, which is the university in Abu Dhabi. And today we will discuss our solution for both problems, for challenge 1 and challenge 2, because in the beginning the metric was a joint metric for both challenges. It was like 70% for challenge 2 and 30% for challenge 1, and we achieved first place in this joint metric, but then it was decided to divide those two leaderboards, and today we will talk about how we get to that place and how we managed to solve the first and the second challenge. Oh, yeah, I see the slides are already on the screen. We will skip the slides explaining the data set and the problem itself because it has already been talked about a lot. So for the first challenge, the first idea was to just use a simple regression model. It is quite lightweight, very fast training, efficient net like 1D convolutional neural network, which use channel squeezing, time drop down, and so on. And I think most of you have tried working with similar-ish kind of architectures. So it did quite well, surprisingly. It beat the benchmark, and in the early days of the challenge, it managed to get high on the leaderboard. But we felt that the temporal dependencies could be modeled more explicitly, and so. Yes, and what we did, for each trial, we kept a 5-second EEG window during the pre-processing, and we had this temporal jitter around 2-second original segment. In order to slightly change the EEG window. And we noticed that when using our previous regression model, the model did not understand that the answer is in the timing of the signal, not in its shape. So we changed slightly the window, and the waveform changed just slightly, but the label, the exact time of the response changed significantly, and the model couldn't just catch it. It was overfitting. So that's when we came up with the segmentation problem. So we decided that, it's not working really well. And about that, my colleague Anwar will say a bit more.
Yeah, hello again. So from my perspective, it's the most interesting part of our solution. So we transform a regional regression problem into the segmentation problem by converting the reaction time label into some kind of smooth segmentation label. When we have, for example, instead of talking that we have the reaction time at time being 57, we could say that we have high probability that actual reaction time was around time being 57, with lower and smooth probability around this value. This takes the problem kind of more smooth and easier to optimize, and give us a lot of value for improvement, and also it's some kind of gives the to model the opportunity to understand that the actual signal should be found inside the time, not just in the structure of EEG data. So we transform it using this Gaussian formula. The model itself was inspired by UNet model, segmentation model. We made it 1D. We made it time distributed. Also, we use some kind of different cocktail of different loss functions. We use the cross entropy, Wasserstein loss, KL loss, RMSE for regression part, entropy to kind of reduce the entropy and focal loss. Also, we have some experiments with hazard. Also, big gain give us experiments with augmentations. We use really aggressive channel dropout, time dropouts, scaling, Gaussian noise, and mix-up to improve generalization. Also, in the end of the training, we use temperature calibration. It was important, especially for kind of stacking different models. Regarding model architecture, so we takes the kind of input signal and return the per time logits like for every object we have 200 predictions. And you can see on the image the approximate architecture of our solution, and on the second image you can see how we kind of treat the predictions using soft argmax. Regarding the next experiments, Ayana could continue the story.
We didn't stop at a single UNet architecture. We built a zoo of models. So it was like wide, deep UNet, lighter UNet variants, an attention UNet with like self-attention in the bottleneck, an Inception style 1D architecture with multi-scale temporal kernels. The goal was to achieve some model diversity because some architectures perform better on like clean, easy trials and other on more noisy or rare patterns. Yeah, and also you can see that those models are very lightweight. That was important for further processing and assembling. And the main takeaways for RT prediction was segmentation style models were clearly outperforming plain regression, and YUnets were most accurate single models standalone, but lighter models bring important diversity component. And temperature calibration on top of these models gave us an additional improvement of the metric NRMC again. And further, we decided to stack those models. Each model output P of T, so from logits, from what we built, and from that one, we built some meta features, let's say, such as soft argmax, variance, entropy, quantiles on other shape descriptions. And for each trial, we collect these meta features from all models using out-of-all predictions to avoid leakage and train a meta model, which we used just a ridge regression or GBDT and predicted response time. GBDT's gradient boost decision trees. And so the intuition was that different models are reliable in different regimes, and the meta model learns how to combine them based on the shapes of their output distributions. Here you can see the stacking results and the comparison between the best single calibrated models, manual blends, ridge stacking, gradient boosting stacking, and so on. Stacking, especially GBDT, gives the largest improvement, both on validation on the leaderboard. So for the task one, the key ingredients were RT as time distribution, transforming that to time distribution, diverse set of our segmentation models, and a well-designed stacking layer. So that's when we can get to our second part of the challenge, externalizing factor task. Just a reminder, we were aiming to predict the psychopathology factor, which was externalizing factor by 2 seconds EEG window, randomly sampled from subject. And to capture this, we decided to, can you go to the next slide, please? Yeah, sure. So the core idea which we get was the brain state at some time point t influences, obviously, the state at the time t plus some time lag. Because your brain state at point T will lead to something and somehow influence your brain state at the further time point. And so we model how xt predict xt plus some time lag using different lags, let's say 100 milliseconds, 150, 500 milliseconds, and so on. And we obtained a compact description of a subject's dynamic connectivity. And our assumption was that those connectivity can be related to the externalizing factor, to the psychopathological factors. What we did next was building two main families of features. One was obtained from lagged cross correlations between xt and xt plus some time lag, symmetric couplings, and the synchrony between the channels were represented during like that. And also we modeled the ridge transition matrices. So like x lagged is a time xt, gets some features out of that. So for instance, the diagonal of A measures some self-persistence, off diagonals measures some cross-channel influences, A minus AT captures asymmetry in the feedback loops, and so on. And then we aggregated these features into scalar features and just like used it further in our model. Yeah, we do fault splitting at the subject level, balancing the target distribution across faults. We start from a set of top correlated features, like correlated with the final psychopathological factor, and run an iterative procedure. So we bootstrapped training subjects, trained a simple ridge model, predicted on a fixed test fault, and either accept or reject features subsets based on the median NRMC and its scalability across the bootstraps, actually. This felt to like stable feature set and simple but nicely generalized ridge model. That was our main like approach for the second part of the challenge. Apart from this challenge, our further research questions, which we're currently thinking about, is like, can we apply our current like segmentation pipeline to other EEG tasks beyond the like contrast change detection? Can we use the dynamic connectivity features to reconstruct or like impute some bad channels? Because we noticed that during working the data set, there are some channels like obviously 0 and so on. Can we generate some missing tasks for the subjects? Because like if we compare the data set, not the data set for the challenge itself, but the whole HBN data set, there are some subjects who have not all the tasks. And can we generate EEG, which would be like task aware and subject aware? And yeah, can we treat the connectivity features as candidates for like biomarkers, such as psychopathological factors? And all of these, I believe, can be answered further. And we probably can do this by reusing our code. And you can also think about this and features we already built for like this challenge. So this is our team. It's me and Anwar. We are both PhD students at MBZ UAI. We're also the founders of DSML-KZ, which is Kazakhstani ML and AI community. And also Yediger, who's my younger brother, helped us with this challenge. He's an undergrad student in Germany. And as a final note, we would like to thank our supervisors, Professor Steve Liu and Professor Kun Zhang, and also our like colleagues and friends with whom we discussed this challenge the whole October. So yeah, thank you. If you have any questions, I'll be happy to answer.